Please print out problem 86 and annotate this page as we go through the parts of this problem in this video. So let's read through it real quick. We have a function 2 to the x, so an exponential function, which we've been talking about for quite some time. We're going to complete two tables, one for h, where we are given the x values, and then we're going to fill in a table for h inverse, based on what we see in this first table. And then down here, we will plot the points for h, and then plot the points for h inverse on the same grid. This is the line y equals x, which we'll talk about. All right, and then we're going to talk about the domain and range for h inverse based on what we see. So let's jump into Desmos. I'm going to make a table here for h of x equals 2 to the x using the values in the table. Now I think what's going to happen is the table is going to automatically fill these in, but we should be able to do this by hand if we had to. So if I input -3, 0.125 is the value of 2 to the -3. That's the same as 1 over 2 to the third, which is 1/8, or 0.125. All right, we'll do the same thing for -2, -1, 0, 1, 2, and 3. Okay, so we see these dots plotted in purple. We'll go ahead and connect them with a exponential looking curve, like so. Let's go ahead and make this a little bit darker. There we go. Let me add the line y equals x, which we have on the piece of paper. And let's make that dotted. Okay, now we'll make a second table. A 1/8 goes in for x, then -3 is going to come out, and it's going to plot that dot right down here. Okay, 0.25, that's 1/4. That gets input into the inverse function, then output comes out to -2. 1/2 gives us a -1. 1 gives us a 0. 2 gives us a 1. 4 gives us a 2. And 8 gives us a... So those dots are on the graph of h inverse, whatever h inverse is. Recall that these dots are reflections across the line y equals x, which is why that dotted line is in there. All right, and if we wanted to, we could probably connect these with a curve that would look like the reflection of this red graph over that line, y equals x. Now let's answer some questions here. Based on what we see, the domain of h inverse and the range of h inverse we should be able to determine because we know those things for the exponential function. We just know that those things get reversed, right? So for this exponential function in red, the domain was all real numbers. So that would become the range of the inverse function. I don't need to have domain on there twice, all right? So this should be all real numbers, all right? So you can start to see like these y values are shooting downward. All right, if we kept plotting dots, there'd be more going on down. And then as we go to the right, they continue to rise. So the range is all real numbers. Now the domain of the inverse function is the same as the range of the exponential function. And the range of the exponential function was all positive numbers, right? Everything bigger than 0. This red graph never became 0 for a y value, and it was unlimited going to the right, right? So we're going to say x is greater than 0. Positive numbers only. Okay, so this is the beginning information about talking about the inverse function to an exponential, right? We can tell what its domain and range is, and we start to have a picture of what the graph will look like. Okay, I'm going to connect these dots without naming the function. Okay, so there's a complete look of the graph of h inverse. All right, so you can see it's going to continue to grow, even though it looks like it's starting to flatten out. This part gets bigger and bigger and bigger as we go farther and farther to the right, and these y values go all the way down to -infinity. And you can see like the y-axis seems to be playing a role of a barrier. All right, so just like the graph of the red exponential function had a horizontal asymptote of the x-axis, this graph, okay, h inverse, has a vertical asymptote of the y-axis, which is the line x equals 0. Okay, again, what's an asymptote? It's a line that we can make this green graph get as close to as we want, as long as we, in this case, make the x values close enough to 0. Okay, so we have all this information about H inverse without it having a name yet. And that's what we're going to get to real soon. So recall, what do we do? Well, we started with H. We input exponents, and we got out the answer when we raised 2 to that exponent. And H inverse, what's it doing? Well, it is inputting the answer, quote unquote, and outputting the exponents. Okay, so that's what this graph is telling us, right? What were the exponents needed to get these powers of 2? So that's what this function does. So we need to now come up with a name for this function, the inverse function to 2 to the x. Okay, we know things about it. We know its domain. We know its range. We know it has a vertical asymptote, x equals 0. Now, if we were trying to do this algebraically, find the inverse function to y equals 2 to the x, our steps tell us flip-flop the variables. So we would have x equals 2 to the y, and then we would try to solve this for y. But there is no algebra out there that allows us to solve for y, right? I can't like divide both sides by something, multiply both sides by something, take the square root, right? Y is stuck up there as an exponent. So we have an issue here. And what we're going to do is basically invent a new word that's going to mean what we want to have y do here. So if we translate this into English, y is the exponent of 2 that will produce x. That's what this is saying right here, right? Y is the exponent for 2. And when you raise 2 to that exponent, you get x, right? That's what we want y to do. And there are possibly better ways to, or better symbols to do that, but this is what was decided upon long ago, all right? So the exponent for 2 that will produce x is given this symbol here. Log, which is short for logarithm, okay? Logarithm, which is Latin or Greek for certain words that fit together here, all right? So y is the logarithm with a base of 2 that produces x, right? So that's how we read this, right? Y is the exponent. Instead of exponent, we chose logarithm, okay? And we need to get used to this notation because it's a little goofy looking, right? So let's just do some examples from our table, from our graph, okay? We would say log base 2 of 8 equals 3. Why? Because 3 is the exponent for 2 that produces 8. All right, so this is the base, this is our exponent, and then this is like the answer when you raise 2 to that exponent. That's how this pans out here. All right, so remember, this is the exponential function's inverse, right? So when you had 3 comma 8 on the original, now you're going to have 8 comma 3 on the inverse. All right, another example. Log base 2 of 2 equals 1. Why? Because 1 is the exponent for 2 that will produce 2, right? 2 to the first is 2. All right, and we'll look at one more, and then you'll get a chance to play with some of these on your own in our next exercise. Okay, this is a tricky one. Log base 2 of 1/4 equals -2. Okay, why? Because -2 is the exponent for 2 that will produce 1/4. 2 to the -2 is the same thing as 1 over 2 to the 2, which is 1/4. All right, so we had to have a name for this function, and now we have a name for this function, right? We have a logarithm. Got to tell you what the base is, so we know whose exponential function we're finding the inverse for. The input of this function is the quote-unquote answer, and the output of this function is the exponent for that base that will produce that answer.